All right, by now you should know all different types of derivative rules. You should be able to take the derivative of all different types of functions, including implicit differentiation that we learned in last section. In this section, 4.2, we're going to talk about the derivative of inverse functions. Now, if you recall, an inverse function is where we switch the x's and the y's. Inverse functions are also symmetric along the line y equals x. You can also think of inverse functions as kind of undoing each other, like multiplication and division, addition and subtraction, squaring a square root. Those are all examples of inverse functions. Now, there's a couple of different true statements that we can say about inverses. One of them is Theorem 3.16. It says that if f is a function whose domain is in the interval, if f has an inverse function, then the following statements are true. So, if f has an inverse function and f is continuous, then that means the inverse is also continuous on that domain. It also says that if f has an inverse and f is differentiable, and make sure that the derivative there isn't equal to 0, if that's the case, if f is differentiable on that interval, then the inverse is also differentiable. Okay? Another thing we can say about inverses is there's a little trick, I guess, that's a Theorem 3.17, that helps us figure out the value of the derivative of the inverse, with or without the actual inverse function. It's a little bit complicated to read right now, so let me show you a quick example and maybe how we could use this theorem to help us find the value of the derivative of the inverse. So if you look with me at example number 1, we have a function, f of x equals the cube root of x plus 4. And it's asking us to find not the derivative at 2, but the inverse's derivative at 2. So we want to find the value of the inverse's derivative at x equals 2. So if we have the function f and we can find the inverse function, then we can find the derivative and plug in 2, just like we've been used to. So remember that derivatives, we can find, the inverses, we can find the inverse of a function by switching its x and its y. So if my original function was f of x, or y equals the cube root of x plus 4, we can use this original function f to find its inverse by switching the x's and the y, and then resolving for y. So I'm going to cube both sides, I'm going to subtract 4, and this gives me the inverse of f. So my inverse of f is really x cubed minus 4. Easy enough, right? I can find the inverse by switching the x and the y and resolving for y. Now that I have the inverse of f, x cubed minus 4, I can easily find his derivative. We've been doing that lots of times, right? By using my power rule, and I can say that the derivative of the inverse is 3x squared. The question is asking me to find the derivative of the inverse at x equals 2. We know that we can find that value by simply plugging in a 2. We can plug in a 2 to the derivative value of the inverse. I end up getting that the inverse's derivative at x equals 2 is 12. Are you okay with that? All right, let me take a second though and compare what would happen if we couldn't find the inverse. Could we still figure out the inverse's derivative at x equals 2 without actually finding the inverse function? So what this theorem is saying, 3.17, is saying that if f has an inverse, we're going to call the inverse g. I can find the value of the derivative of g, the derivative of the inverse, by first finding the value, the derivative of f at the y value of the inverse and then reciprocate it. What? Okay, let me take it step by step. If I have a function, my original f function, remember, was the cube root of x plus 4. Can I rewrite that as x plus 4 to the 1/3 power? So this is, again, remember, my original function f. if I can find the derivative of f, which I can, using my power rule with the chain rule, I can bring that 1/3 forward, keep the inside the same, subtract 1 from my exponent, and then don't forget to take the derivative of my inside, which happens to be 1. So the derivative of my original function, if I simplify it and bring down my positive, make positive exponents there, I get that the derivative of f is 1/3 times the cube root of x plus 4 squared. Now that's the derivative of my original. But remember, the question is really asking me to find the derivative of the inverse. If I go back to the theorem, I can try to figure out the value of my inverse's derivative if I know the value of my original derivative at the y value of my inverse. Because remember, the x and the y's are switched, okay? So what this is saying is that I know the x value of my inverse. The x value of my inverse is 2. But if I'm trying to find the derivative of my original, I need his x value, and I don't have it. I only have the x value of the inverse. But remember, inverses and regular original functions, their x and y values are switched. So if I know the x value of my inverse, isn't that the same as the y value of my original function? So I know the y value of f. Could I figure out the x value so that I can find his derivative at that x value? Well, if the y value of f is 2, I should be able to use my equation of f, my original f of x equals the cube root of x plus 4. And if I know that y is 2, I should be able to plug in a 2 for y, and I should be able to solve that equation to get his x value. I can cube both sides, I can subtract 4, and if the y value of f is 2, then that means his x value is 4, right? So now that I know the x value of f, I can use that to find his derivative value. Remember, my derivative was up here of f, and I can find the value of the derivative of f at 4, not at 2. His x value, remember, is 4 now. So the derivative of f at 4 is 1/3 times the cube root of 4 plus 4 squared. I'm plugging in a 4 into my x value in my derivative. 4 plus 4 is 8. I now have the cube root of 8 squared. I can either do 8 squared and then find the cube root, or I can do the cube root of 8, which is 2, and then square it, which is 4. 4 times 3 is 12. I end up getting that the value of my derivative at 4 is 1/12. Now, why did I do all of that? Well, what this helps us do is look at this theorem and figure out, kind of dissect it and figure out what it's really saying. What do you notice about the value of, let's do green, the value of the inverse's derivative at 2 versus the value of the original derivative at 4? Remember, the x's and y's are switched, but what do you notice about those two answers, their derivatives? Hopefully you notice that they're reciprocals of each other. And that's exactly what the theorem is saying, that if I can find the derivative's value at the y value of the inverse, right, because their x's and y's are switched, it's always going to be the reciprocal of the inverse's derivative at his x value. Okay, so again, the value of the original function at his x value, the value of the original function's derivative at his x value is the reciprocal of the value of the inverse's derivative at his x value, which happens to be the y value of the original, right? So that's what the theorem is saying. Now, in this example, obviously, it was probably a lot easier to just find the inverse function from the beginning find its derivative, and plug in 2, just like we did before. But what happens if I give you this example? Look at example number 1b with me. If I give you this function, f of x equals 1/4 times x cubed plus x minus 1, and I ask you to find me the value of the inverse's derivative at 3. I want the derivative of the inverse at his x equals 3. So if I try to do it the same way as I did in the last example, the easiest way was just to find the inverse function. Remember, we can find the inverse function by switching the x's and the y's. So I'm going to take my original function, I'm going to switch out the y for an x and the x's for y's, and now I want to resolve for y so that I can get the inverse function. Ooh, that's a little bit harder, isn't it? This function is a little bit more complicated. You might notice that I have a y cubed and a y, and it's a lot harder to solve for y in this equation, much harder than it was the first example. So because it is too hard for us to find the inverse function, what we can still do, we can still solve this problem. We can still find the value of the inverse's derivative without having to know the inverse function. I can find the value of the inverse's derivative at x equals 3 if I know this theorem, the 3.17. Remember, it says that I can find the value of the inverse's derivative at 3 if I can find the value of the derivative, the original derivative, f prime, at his x value, which is really the y value of the inverse, right? So when x is 3 in the inverse, the y is 3 in my original, and then it's just the reciprocal of that. So here's what we have to find. We've got to figure out what x value we're talking about if we're talking about the original. I know the x value of the inverse, it's 3, but I want to find the x value of the original. Remember, if the x value of the inverse is 3, then that means the y value of the original is 3. That's going to help us find our x. So if I know in my original equation that y equals 3, I should be able to plug in a 3 for y in my original equation and figure out what x is, so that I can plug that in, that x value, into the derivative of the original. Now again, this is kind of hard to do by hand because again you have an x cubed and an x, and it's hard to solve for x when you have that. So here's where we're going to have to kind of cheat it a little bit, and we're going to have to use our technology, our calculator, to find x. So that's what I'm going to do. I'm going to pull up Desmos. And in Desmos, you might see that I have my original function plugged in. I have my f of x equals 1/4 x cubed plus x minus 1. And remember, we want to figure out when y is 3, what is our x value? Now, there's a couple different ways you can do that. You can kind of look at the graph and kind of estimate. But we really want to figure out when y is 3, what's the exact value of x. And you might be able to kind of eyeball it and see on the graph. But what I'm going to do, and there's a couple of different ways you can do it, is I'm going to plug in another function. I'm going to plug in g of x. And I'm going to say that g of x is equal to 3. So I have an f of x, which is my original function, and I have my g of x, which is equal to 3. And what I want to do is I want to set them equal to each other. I want f of x to be equal to 3, right? Well, I can figure out their solution, the x value, by figuring out their intersection. This is like systems of equations back in algebra. So I can see on my graph that when y is 3, my x value is 2. That's perfect. That's exactly what I need. Now I have the x value of my original. My x value of my original when his y is 3 is 2. Okay, so let's go back here. So now I know that when y is 3, my x is 2 in my original. So that'll help me with my formula. I can find the value of the inverse's derivative at 3 if I know the value of the derivative at 2. Remember switching the x and y's? So now I've simplified it down to the value of f prime at 2 and then his reciprocal. So now we still have to find the derivative of f. Once we find the derivative of f, I can plug in 2, reciprocate it, and that will be the value of my inverse's derivative at 3. So let's find the derivative of f. Remember, if f is my 1/4 x cubed plus x minus 1, I can find his derivative. And then I want to plug in 2, so I can find the derivative of f at 2. I end up getting 4. So if the derivative's value at 2 is 4, then that means the inverse's derivative at 3 is 1/4. Remember, they're reciprocals of each other. I can find the inverse's derivative at x if I can find the original's derivative at his x, which is the y of the inverse, and then reciprocate it, right? Even without knowing the inverse's function. If it's too complicated to find it by hand, I can still find the value by using Theorem 3.17. Practice that. It'll get a lot easier, a lot less confusing the more you practice.